So it's my pleasure to introduce Prakhar Garg, who's here to talk to us about gaseous detectors and the work that he's been doing in R&D and construction of in various experiments. And so he is one of the lead people for the CPC that sPHENIX is going to be used, and we should congratulate him. It got shipped to Brookhaven last week and is there. Seems to be working. So sPHENIX will take first data in March or so. Just online. And I guess we will hear more about it.
Awesome. Thank you, Helen. So, as you can see, I will be talking about the gaseous detectors for the upcoming and future experiments. And I decided to call it gaseous, not MPGD, because there is a technology I'm going to talk about, which is not really MPGD fully. So that's why I said, okay, let's call it gaseous. So that's like the outline of my talk. I will give like a brief introduction, very preliminary, just to refresh the memory. And then we'll talk about mainly 4 experiments where I'm currently involved and at some level. And as you can see, the timeline is very standard because really it's very hard to work on like 4 experiments at the same time unless they are different times. So as sPHENIX starts this year, the construction has been finished. I will talk some things about as sPHENIX TPC. And then the GridPix proposal for the EIC, which recently got approved, but the application part of it is we are looking like 2030 down the road. And then there is a MOLLER gem tracker. I found it very interesting how they use gem detectors for MOLLER. So that's why I decided to talk a little bit about that and about the motivation. And that's sort of 2025 timeline. And then there is a Pioneer tracker, which is 2028 timeline, in which we basically are the primary people for the tracker of the Pioneer. And then in the last, just to summarize what I was talking about. So a very quick look at what happens when a charged particle passes through the gas. We all know it ionizes it, and with it interacts with electromagnetic interaction, and the incoming particle ionizes and excites the atoms of your gas, and it interacts with the medium, and that's kind of leaves the signature in the gas volume. And then there are other physics processes as well, like Bremsstrahlung, Cherenkov, transmission radiation. But the energy deposited in gas, because of these interactions, are very small. So that's why we don't talk about these energy losses when we talk about it. A DEDX device as an example for LSF or TPC. We just talk about the ionization energy loss, not the other losses, which might be there, but they're very small. So we typically ignore them. So typically, when charged particle goes, it first knock out an electron, which we call a primary electron. And then this electron further leads to other secondary ionization, which are called the secondary electrons. And then there are delta electrons, like very high energy electrons. So one of the important things here to note is the delta electrons are one of the notorious things. You don't want them because they sort of trouble you. And secondary electrons are also troublesome, as I will discuss a little bit. What is it?
No, you're right. It's just we have a gift for you once you leave us.
Okay. So, and secondary ionization is also notorious, especially when it comes to DEDX device. I mean, I will briefly talk about them. So only primary is good, but nature is not so kind to us. You never got just primary. You have to deal with the secondary too. So if we look at the historic context, we all know GM counter, the gas target cathode wire, charged particle goes, and there were limitations in time and the resolution problem. But what happened eventually as the technology also advanced, when things became more compact and engineering became more reachable and possible, this MPGD technology sort of boomed from there. And there were like so many ideas, like MWPC, which was sort of started by Chalpa, who got a Nobel Prize also for it. It got the application in TPC right away, and Star TPC and LSTPC both use wires for a long time. Well, Star also have like inner upgrade, so now they have Jam plus wires, but Alice has totally moved to the Jams from the wires. But that's how they picked it up. And then you have micro strip gas detector, gas electron multiplier. So they are all microstructure. The idea is that you apply some voltage, and because the structure size is so small, you will have a lot of electric field strength there. And once you have enough electric field strength, you can make the avalanche. You can sort of multiply your single electron into many. So now there are many clever schemes and many clever methods, but that's basically the fundamental of all the NPDB-based detectors. So as I was saying, there are many flavors of micropattern gas detector. So as an example, if we look at this jam as an example, so you have an insulated kapton layer in between and the copper sitting on top and bottom. You apply some voltage, and then there are electric line of forces. You can see here there is just more number of lines in the hole. That means you have more electric field intensity there, and which will produce an avalanche in your detector. So there are many things, and they all have their advantages and disadvantages. Like micro-RWELL, they have some advantage. You can put them in any shape. They are like spark protected. They are more robust. Micromegas have different applications. So the reasoning for most of these different designs and configurations was depending upon the need. Like I want to do something like this with that, but it won't work. So they develop something else. So a lot of these developments goes around the need of like what you actually want to do with them. So now since most of the detectors I'm going to talk are gaseous detectors in one way or another. So I will start with the sPHENIX TPC, which is sort of the project that just finished construction, and the results will come in future. But you can see here is an event display of one of the cosmic tests we did at Stony Brook, and that's how you test it with detector box and all. So a little bit about the sPHENIX experiment. It has a 3-year run plan. It is supposed to start this year, and as you can see, like 3-year run plan is really short. So their physics goals are very limited. Like it's not like Star or Phoenix had been, where they had a very extensive run plan for decades. But if you look at the detector, they have all the important ingredients one can imagine in a heavy ion experiment. Although the running is not long, but the detectors are all in place there. And as you can see here, the vertexing and the inner tracking is done with the INTT and MBTX, and then comes the TPC as the main tracker, and then comes the inner HCAL, EMCAL, inner HCAL, the magnet which we borrowed from the Babar. It's a 1.5 Tesla magnet, but we decided to go with 1.4, not to the full strength. And then there is the outer HCAL also. So the one point here is to note is this: the TPC is not a DEBX device for sPHENIX. Traditionally, in Alice as well as in the Star, both use TPC as a DEBX device, especially for the low momentum globe, 800 MeV or something. But sPHENIX TPC does not have the goal to do any PID, because the physics program does not require particle identification. So the application of TPC is to do high resolution tracking only. That's the only goal for the sPHENIX TPC. Here is just to flash what are the 3 or 4 regions they are looking mainly. One is the Flaconian spectroscopy, because even Star or Phoenix, well, Phoenix has no hope, but star even could not separate 1s, 2s, and 3s states, and that's one of the thermometer, if you like, for the QGP evolution. And they want to understand how the yield of these three states change when you do as compared to PP to gold collision. And that's where, and we are interested in only the dielectron channel of X7. So that's why the TPC tracking is only limited to dielectron, like electron and positron, not the muon channel. Right? That's where mostly TPC application comes in, but also of course for the jet structure and the pole fluidity and the particle energy loss, good tracking always helps, so it cannot hurt. But the requirement was to get the high resolution mass resolution for the X7 state in the TPC. So if you want to put TPC in simple words, I don't think I need to talk too much about it, but basically particle goes in, it ionizes. If you have a magnetic field, it bends. If you can measure the magnetic, if you know the magnetic field precisely, you know the curvature, you know the dimension. And that's all sPHENIX TPC is designed to do. Now here on the left, I show the AutoCAD model of the TPC. So as you can, it looks like any other TPC, basically. Two end plates, they have the readout set, and at the center you have a center membrane where you put the high voltage and then you drift towards the end. Now, a couple of interesting things, particularly with this TPC, is this. The star and Alice TPC, just like, because they're running examples, the sizes are very large. The star TPC is way bigger than sPHENIX TPC. I mean, you can think it's like clouds, which is like 6 feet, can actually fit, matches the TPC. That is small the sPHENIX TPC is. That's really a challenge if you think about it, because the potential at the cathode is like 45 kilovolt or 50 kilovolt. And you want to insulate it also from the ground plane. And in star analysis, they use the distance just to, oh, there is like 1 meter of air, I want to spark. So that's easy for them. But we did not have this option to have a very good insulation. So there are many cute engineering things which we did with the sPHENIX TPC. Some of them I'll show in the following slides. But another noticeable thing is the readout plane was not Cartesian, it was a polar coordinate system. So that helps you with the dead area and to reduce the dead area as much as possible, because you want to have as many samples as possible without losing too much information. So we had very tight constraint on the acceptance, like physical acceptance of the readout. So the readout plane is Cartesian coordinate. And another cool thing about the readout is we use the zigzag pad structure rather than like a trapezoid or hexagonal or a stripe or anything like that. And the benefit is, as you can see, that if your charge cloud lands on this, it will go to like 2 or 3 zigzag stripes. So if you do the calculation with a weighted mean, you get much better resolution as compared to a stripe where it's just delta over square root of 12, which is your resolution. So zigzag pattern really helps to bring the resolution to a good number. And another benefit is you reduce the channel count. Because these zigzags, as you can see, like there are like 16 sectors, and the length of the zigzag is 1 sector. So they are very long in R, but very fine in phi. Because what you care is the phi resolution. The R is the sampling, right? I mean, once I get a sample on a pad row, I'm happy with that. So that really helps with the number of channels. And another thing, the quad jam gain stage is basically the same as what Alice did with the rotated jams, right? So to reduce the ion backflow. Or even though it's not big concern for us, but still we wanted to have as low as possible, because it always helps with the calibration to start with a low number rather than start with a high number and then struggle to correct that. So the gain stage is the jam configuration is almost same as Alice. So as I was telling, the field gauge is manufactured in this schematic picture. You can see there is a carbon fiber which works like a ground plane, because carbon fiber is a conductor. Then there is a honeycomb structure. It's a half-inch honeycomb, which is for stiffness. And this honeycomb was also customized. It's not on-the-shelf honeycomb. It has a feature to bend only in one direction. So if you get a sheet of honeycomb, you will try to bend, it will just bend in the cylindrical shape, not in the other direction. So it really improves the stiffness of the field gauge. And it's only half-inch honeycomb, so it's very sleek. And then comes another carbon fiber sheet just to give the stiffness to the honeycomb structure. And then there's a layered kapton. So one layer of kapton is like 5 mil, which gives you like 7 kilovolt per centimeter insulation. So if you put 18 of them, that helps. Now that's the trick. No company manufactures a 3 millimeter width of kapton of this wide, right? So that means you have to make yourself. The issue is you will say, oh, you can buy a roll and just wrap it around. But if you got air in between, that will be bad, because then you're sort of weakening your strength of the high voltage holding capacity. So the very cute thing, and I would like to share it with you guys, is the helium is a small atom. So helium has a very good permeability to kapton. So what we did, we put a tube, just any random plastic tube, made a hole in that and run helium, run rapid. So we are intentionally replacing air with helium. And then you come the next day and you see the color change, because all the helium just escaped overnight. And this way you can really get rid of any air bubble whatsoever. So it worked out extremely nice. And of course, we tested it for high voltage. Here you can see, thank you. Here you can see like the alignment of the stripes. So these stripes, again, when you are in a small volume, any imperfection you cannot handle, you cannot bear, because you just have very small volume. So everything needed to be extremely precise as compared to other. So that was another cute thing. You see, there is a microscope which is mounted on the card, and you look on a screen. So a stripe which is like 2 millimeter looks like this big on a big screen. And then you put a cursor on that, and if you rotate your field, you can actually align the stripe. So the precision you can get is like 10 micron by hand placement. It's no machine, it's the person. Well, in this case, it's me. But by hand, I'm looking at the screen and adjust the stripe. So it's extremely precise. And this is the picture after we put together the inner and outer field gauge from the bottom when the cathode is still not there, so you can see the top from the bottom. So this worked really well. We have tested it, of course, for high voltage, and it holds. So again, similar to Alice, as I was saying, like you have 2 large pitch jam coils and 2 small pitch, 140 micron and 280 micron jam coils, and they are rotated 90 degrees to avoid the MOLLER pattern, so that you get more or less uniform gain. All those tricks are used. Only the readout, actually this is a picture shown by some Alice presentation. We just changed the readout because it's identically same. They had the square pads here, we just put the zigzag pattern. Hereby is identically same. Another cute thing is the way the high voltage goes outside the world, we do not solder any resistor in the gas volume. So the current limiting resistors are sitting in these slots, which are also potted with epoxy. So there is no line of sight to any of those resistors. And the high voltage connection which comes out from the jam goes outside world. We call it a tail. So as you can see, they are like copper traces. And another cute thing about these copper traces, if you have a solid stripe of copper and you try to bend or do anything with that, you will tear it out right away, because copper is a soft matter. You make a mistake, it will tear out. So there is a technologically developed, established thing which is to make the pattern of a hexagonal on the spine. So even if you start it here, it will not propagate. It will break one hexagonal, not the entire connection. Well, and it was true. Out of all the module production, we never had any issue of tearing. So it's very strong, very stable, and it just works nice. So here again, one of the test beam results from 2019 test beam, and many of you are participants of that test beam. And as you can see clearly, so in formula we don't have magnetic field, so resolution you have to get without the magnetic field, right? So this curve shows the resolution as a function of drift length, because as you increase the length, the diffusion spreads your cloud and your resolution gets worse. So it's a normal trend. And then mathematically, if you know what's the diffusion in a magnetic field, you can get your resolution back in the magnetic field. So this dotted line here shows what the resolution will look like if you just use the same detector into a magnetic field, because you have reduced the diffusion. And as you can see, for 100 meters, which is one side of the EPC length, for 120 to 110 centimeters, the resolution is already 120 micron, 110 micron, which is pretty good for the excellent program, especially. There is a little story I wanted to definitely share. So we initially started with neon CFO 1910. That was the gas mixture we used, but we rejected because there was a high attachment. It just was not stable. So we rejected early on. Then we switched to neon CFO 5050. Nikolai was one of the main driving force there to decide the gas. And I was doing the simulations a lot at that time for these different gases. So we settled on 5050, looked good. And we keep running, the test beam results were good, we were happy, the chamber was stable, everything was good. And then Ukraine war happened. And guess what? Neon was out of market. The cost of a neon bottle is $30,000 right now for one bottle. When Nikolai has some.
From my left.
It's extremely expensive and rare to find. Well, so then we have got in a problem. Like, okay, but what you do, because gas is the main element of a detector, you cannot even continue with testing the gain map, IBF maps. We have to stop just everything, because if this is not the gas you're going to use, you cannot do anything. So we were quite stuck for some time, but we were fortunate enough to find out another gas, which is R1CF46040. And the whole the parameter space of gas was to find identically almost same gas in terms of drift velocity, in terms of diffusion, in terms of attachment, in terms of Townshend coefficient, find the best possible gas which is close to, and we found one. And then when we tested, and basically all the gain map, all the IBF were done with this gas. And we seemed quite okay with this gas also. So we came out of it, but it was a big hit on us for a month or two until we figured out. But now this is the final gas we are planning to go, because there is no hope to get neon in next 2-3 years. No way.
Prakhar, only one problem
Yep.
is this gas compared with neon. Ions moving 3 times slower.
True.
Unfortunately.
True,
It means
true.
all space has distortion grow up.
Yeah.
Oh, but that's already a foreseen, even with neon, wouldn't that have been a foreseen problem?
Neon is 3 times faster moving than arc.
Right. The ion mobility.
Yeah, but I guess I'm just saying, if we think it might be a problem with neon, and then it gets way bigger with,
The neon is better.
Neon, of course, is better. It's
Yeah.
not,
Because so the thing is this, you want to have your ions to move as fast as they can. Right? So these ion mobilities depends on the combination. It's like a resistor in parallel, if you like. You have mobility in K1, K2, and then you add them in resistor in parallel, and that's how you get that mobility. It's called blanks here. Neon is lighter, right? So it contributes to that ion mobility, and they're always faster than heavier gas like argon. That's, I think, what Nicholas.
But then will the space charge distortions be like a problem for sPHENIX?
Well, so that's an interesting question. How big problem they will be for sp? That's an interesting one. But I will point out at least 3 things we did to help with the ion mobility. Number 1, our drift velocities are 400 volt per centimeter. L is star maybe 110, 130. So if you increase the electric field, ion has to move fast. Their charged particles have to move faster, right? CF4 helps tremendously with the mobility also. So CF4 takes you in the right direction in that sense, right? And number 3, we are not very much concerned about the DEDX fluctuations because IDF really hit very badly to the DEDX. So since DEDX is not our primary goal, we will have to see how the data looks. But right now we have no choice. There is no way we can use neon. And you cannot go down from there because then you lose ionization. You cannot just have any operating gas besides argon at this time.
So sorry for that. Since people interrupted, maybe you can take a step back for some of the newer people in the room. Like, I'm not sure if they've caught the difference, like when you talk about the mobility versus the drift velocity versus you just said IDF.
I see.
How are we matching between those two? Or what
Okay.
effects do they have?
So I can say something about it. So IBF is ion backflow, right? So that means in a let's say you have a gas detector where you have like 4 ion stacks, and your primary comes in, you avalanche, and then you G down. But during avalanching, you are producing a lot of electrons. Well, that means you're producing a lot of ions too. And where all these ions will go? So a lot of them wants to go at the bottom of your jam point, as an example, because that's where the drift lines are, right? So they hit. But still they escape. They make through the holes and go back. So even if you have a tiny, and remember, these are high rate experiments. The collision is happening at like 15 kilohertz, right? So you're constantly pumping ions, and they are slow. So what happens, eventually you have 10 kits of ions in your detector. So when a primary electrons come now, it says, oh, there's a lot of positive charge, let's wander around and wander around and wander around. And you just totally lose the information of this primary ionization, right? So that's what IBF means. And so if you don't know, if you can't measure the energy deposited by a track, means you cannot count the electrons properly. You just lose that information, right? So that's what we mean IBF. So ion mobility, when I say is, so if it's a charged particle, it will move in an electric field. So what will be the velocity of it? That's the mobility times the electric field is strength, right? So that's why I was saying, if you increase the electric field, you sort of move it fast, and then you are gaining on the time, and ion takes to reach, right? So that's what I. And when we call drift velocity, because so what happens when an electron is placed in a certain electric field, it acquires like a terminal velocity. It does not accelerate after that. If your electric field is constant, your electron will reach to the distance with a velocity which we call a drift velocity, right? So how much time it takes to drift an electron from the ionization point to the dark field, right? So, and also you can see here like the transverse diffusion, which is the green and the open green markers. The diffusion really goes down when you put magnetic field, because magnetic field really pinches the electron spread, right? So they are kind of more focused because they sort of spiral in the magnetic field. So the focusing gets better as they increase the magnetic field.
Can I ask a question real quick? Because I mean, I was going to ask it earlier, but it doesn't have a good time. So with respect to the ion backflow, what I'm curious about, because we ran into this problem with the at least when we were doing R&D and QAs, where we were seeing that the actual ion backflow was generating secondary discharges And this was a problem that we weren't really able to resolve, and we sort of just took it as it was and realized that we might need to, I guess, account for secondary discharges caused by the ion backflow.
Are you sure it's the discharge or are you talking about something else?
I think it might specifically be for
Because,
the discharges.
I don't know.
I mean, we can check.
Yeah, we can chat, but one problem I know is kind of the mirror charge of the ions going up, but that's a different topic. But the discharge, I'm not sure why IBF will cause discharge.
Okay.
I'm not sure.
If I'm not mistaken, question collected your ions on filtering sometimes.
I see,
Maybe this problem.
I see.
I already struggled with this problem. Also, just the charging also destroyed field very close to field.
Right. I see. Okay, that's different. That's not the module, that's on the field page. Okay, that's a different. But that's not really a problem. So here, just to give you an example map, like how the gain and the IBF looks like. So you see there are like candle plot, we call it, because there are 16 segments in our pathway. So if you have a source which is scanning, so what happens on what, let's say this is my pathway and I have a source. Some of the charge is shared by this and this, so you read less current on this path. When your source is centered to the stripe, you read the maximum current because most of the ionization is covering that pathway. And then as you go down, it's the same thing. So that's why the peak value of these currents are the actual gain for that pathway basically. And as you can see in this color plot, so our results are very much comparable to the ALICE. The mean over RMS is like something 18, which is also accepted criteria for the ALICE as well. So we're pretty happy, and the IBF is 0.3%, which is also not very bad. It's not the best, but it's not that bad for our purposes. Just to throw some pictures, like here they are the produced modules you can see, like sitting there R1, there is R1, R2, and R3 size, because it's kind of a wedge to mount. And there you can see when we first time started putting the modules onto the wagon wheel, and it all worked really nice. So there was one very good suggestion actually from Dick Micah when he was the reviewer, and I had to defend in front of him. He was very concerned about the module to module stability. And it was a legitimate concern. He said, you have to test it. Until you don't test, you don't. So because of that, thanks to him, we have like so what we do after the module production, we put a Kapton around the module. There is a Kapton wall in every module. So when two modules sit next to each other, they see two layers of Kapton, which is extremely robust. Like we never see any problem after that. So that was
Yeah, because problem is on the top gem,
right.
voltage is more than 4 kilovolts.
Yeah, it's like 5,000.
So really just of course it's very
Yeah.
careful to do that.
Exactly. So if by any chance you drop, let's say one module, there is a whole huge potential difference. And that will spark. It's hard to hold 5,000, 6,000. But once you have two layers of Kapton, then things are totally different. So that is very good. I mean, we haven't seen any issue since then. Just a quick rundown how we installed. So we had a inner field cage and an outer field cage. So we lift the inner field cage up on a crane. By the way, there was no DNL technician doing it. It was all us. So it was a little scary. Right, and then so what we do basically, you mount all the gem modules on the wagon wheel and then flip the wagon wheel and lift it up. So gems are already in place at this time. And then we bring these two concentric cylinders and just lift it up. As you can see here, they're like really, they're already centered inside. And then you raise them up. And from the bottom here, you can see they haven't made a seal, so you can see through the wagon wheel and the field cage, but they're very close. So this is also very new thing, like the seal is not O-ring, it's spring energized, so it's a different kind of seal. So it's kind of a rubber plastic thingy, and then it has a spring, which is like non-magnetic. Because when the magnet quench, it's not nice for your detector. So you don't want the O-ring pulling out your entire hand, right? So you have to be careful there. So it is very strong. It's very hard. It's not like you can press anything by hand. You have to put like tools to press it. It's extremely hard, but the good thing is it makes a very good seal. So even with a very tiny gas flow, we can have a bubbling on this TPC. So there's almost no leak in this TPC, which is also quite some. And then once it's bolted from bottom and top, then there is a 80-20 beam. You rotate it like on a shaft. And then there was a card there which is supported and will be has been transported to PNL already. And then there are rollers which just slide on this tube, and then you lock them so that it don't rotate or slide. And there it is ready after the installation. So it was quite an interesting operation.
How many replacement chambers did you all produce?
So we need 72, 36 on both ends, and we actually had 90.
Okay.
But I would say, since there are many stages of quality assurance, like, if one of the factory said there is a large leakage current, they rejected the foil.
Sure.
So by the time we got the foils and we tested the modules, most of them were good. So we had only 4 modules which showed a spark after production. So none of the module really showed a problem because of there are many already QA steps. There's a high voltage testing on each foil. There's a leakage current testing on each foil. Then we will do our own high voltage testing before we assemble. So there are many checks. So by the time we get there, we had not really many spark big bodies. This is another some. I just wanted to flash one thing. I think I'm running too late. I wanted to just flash one thing, like most of the cooling things for the TPC are done very neatly. Typically, people insert this electronic card, PCB, and try to cool the PCB, right? Run water on PCB and stuff like that. What we did is a very different approach. So our PCB card is small, and then there is a larger aluminum plate. So you do not insert a PCB card, but you insert an aluminum plate into the slot. And all these slots are then connected with a gap pad, which is a highly thermal conductor material. So once the plate touches the wedge, it's cooled. There's like the connection is like awesome there. And these water lines are not running on normal pressure, they are running sub pressure. So less than the atmospheric pressure. So if you poke this cable, the tube out, nothing will happen. Water will go in. So even if you have a disconnect or something bad happens, it will go in, not out. So it's almost a very small chance of leakage or any such thing. So that all works really well. So this is again a collage of different pictures. That's what I was talking about, the gem tape. This is our X-ray scan, which one of our MSI student built. That was his thesis basically for masters. And there are some pictures of the PPC and some playing around with the sPHENIX card and the electronics. So sPHENIX TPC at SVU, that's how it looked after doing most of the wiring. Still the opticals are not connected, only one sector, because they are fragile and we did not want to connect them before we transfer. So now they are all connected at BNL. So and it will be inserted next week into the PHENIX. So yeah, so that was for the sPHENIX. Now comes the GridPix detector. So for the EIC, electron ion collider, I think most of you have heard about it. It has been approved to be built at Brookhaven National Lab. They already have an existing collider, as we all know. So the idea is to add another electron ring to the existing facility, so that we can have electron and the proton or electron and ion scattering. So GridPix is kind of a tracking and a PID, both detector, and I will talk more how it does that. But before that, what's the kinematics for the EIC physics? So basically, if you look at this diagram where the hadron beam comes on the left, electron beams come on the right, you do stacking, and then depending upon where you are in X and Q square, you have different particles in all basically every acceptance. So they are interested in forward, backward, and that all three. So that's why they need a hell lot of detector technology in every possible direction and every possible capability. So that's why EIC detector is really a piece of art, and it's a real challenge to put together something which can do everything in a nice way. So just to motivate, what are the particles coming out of all the EIC spectrums? So this particular one is for the pions, but it's identically similar for the proton and kaon also. And as you can see clearly here, there is a lot of particle production, even at very low momentum, right? At 1 GeV by C, you see there is like a whole red band. So there are particles at low momentum, which you will get at EIC. So there is no bypass to ignore them. You have to measure them. But and here you can see the requirement for that, right? Like so, there was a 3 sigma separation of 5 kp. Forward, backward, and central region have different requirements. But the GridPix we are thinking about is mostly for the central region, the barrel, which has a requirement of 10 GeV by C. Now, it's not just the detector one needs to consider. It's also if you have a magnetic field and if your charged particle bend before going to the detector, no matter what technology you use, you will not be able to identify it, right? Because it will not make into your detector. So one needs to be extremely careful the placement of your detector when you are looking for what is the minimum momentum I can access. And in this case, this is a picture which shows what are the minimum momentum requirements. And if you put GridPix here, it sort of covers a lot of low momentum particles going into that. Now the issue is, now you will say, well, why don't you just put a TPC, right? It does PID, we all know it, and it will do low momentum easily. Now, remember with TPC, the issue is the more the segmentation you have on your readout, the better you measure, right? That means you need as many as possible, right? Now, well, okay, can we do as many as possible? No, because of the diffusion and all those things, and even your amplification state, you cannot really do, there is a limit, minimum limit that you can segment your track, right? You cannot go beyond that. So there is a limitation in terms of TPC. Another thing is also, as I was showing, the wagon wheel you saw, it was aluminum block. So you cannot put that much material in either direction, in the electron going direction as well as in the hadron going direction. It's a lot. You have electronics, you have cooling, you have wagon wheel. EIC cannot afford to have that much material. So TPC will not be good enough. The conventional TPC will not be good enough for the EIC measure. And that's one of the motivations for the GridPix. Here I just want to flash one thing that we all know. When you say PID, you have to measure the velocity. And if you can measure the velocity, you say, okay, I can do PID. And there are very limited ways. Number one is the direct record signal time, like time of flight. How much time it takes, and if I know that, I can tell you which particle it was, right? Because I know the momentum. Or you can do specific ionization EVs and tell as TPCs do that. And then another one is the Cherenkov radiation, right? I mean, by knowing the emission angle of the Cherenkov photon, you can sort of know the beta and then you know the phi. But the transition radiation and James Tolerance, they are the EID mechanism. They're not the PID. So remember, PID means, when we say PID, it's hadron identification people are talking mostly in EIC context. But when you say, I want to know whether it was electron or something else, then it's PID mechanism. So we are concerned about the PID, means pion, chain, and proton separation, not the not the electron with this device. So what are the methods to do? What are the methods typically TPCs do, as I was telling you before? So they use either the truncated mean, where you sample your ionization over a long distance and then truncate the mean and then average them. Or you do a distribution fit, like you do the probability distribution fit, get a Landau, use the most probable value, MPV, and then average that, and you say, okay, that's my GPS. So the fundamental is you want to divide the tail as much as possible. And again, this tail comes from the secondary ionization. So when your charged particle goes to the gas, your primary, which is Poisson statistic. And Poisson is easy. 1 over square root of number of electron you emit is your resolution. It's awesome. But unfortunately, you have secondary ionization, which is not Poisson, which is a Landau. And if you miss your tail, it goes in your measurement, and you are just cannot achieve the resolution. So the benefit of GridPix, as you can see, it's a silicon pixel with a mesh on top of it, like micrometer. And these holes are really aligned to the pixel. So because if you have like a single electron here, you can't sense it. It's not enough charge. So you need to amplify it somehow. So they use like a micrometer style mesh on top of it. So when a single electron comes in, it's sort of amplified, and then you read it out from the silicon. So if now imagine if you have a 25 micron pitch silicon, then you are segmenting your part track to that small numbers. So even if you're like 10 centimeter long track, now imagine how many samples you will have, more than any TPC ever built. Because the sampling size is so small. And that really is the fundamental idea behind the GridPix, that you can really go compact and get even better resolution than the conventional TPC. And think about it now, tracking, we are always advertising it as a PID, but even for tracking is the same. Like sPHENIX TPC, how many space points we have? 44. Alice maybe 200 something, right? But with GridPix, imagine that the numbers are in thousands. So the tracking can be as good as a silicon tracker, and there's almost no material because it's all gas. So it's extremely interesting detector technology, which has been actually pursued by the ILC TPC group, and in the context of LHC also, a lot of R&D has been going on. So the basic idea is it's like a TPC, but the cathode plane is not at the center, it's at the end. And this end is the direction where the electron is going. Because EIC is very sensitive for the electron scattering, because that decides their kinematics basically. So they do not want any material whatsoever in the electron going direction. So if we just remove everything, like there is no readout, nothing, it's a MOLLER sheet of aluminum, think about it. And that's the only material you have on the side. So it's a single-ended cathode. And then at the other end, you have this identically same honeycomb field case we can do, because we have it. And then these GridPix sensors sit on the other end of the readout. And that's the conceptual design we have come up so far. So again, it's the same along the line, like star TPC, as you see, that it can do very good PID at very low momentum, but the problem is large space is required and the material budget. They cannot do that at the ELC. So here are just, I'm throwing some words about the GridPix. It's a 55 micron by 55 micron pixel readout for a gaseous TPC basically. It has been tested in test beam in 17, 18, and 2020, and we are going to do it this year in June at Formula, because it has been approved for us also now. And ultimate DVDX device, because as I said, and the efficiency is more than 90% for the single electron. So the goal is to get enough diffusion to get every electron into a different hole. Because you can imagine the situation when 2 electrons just fall on 1 pixel, and then that would not be good for you, because you will just saturate your electrons, or you will understand it different. But so that's why what you do is you try to have enough diffusion so that your electrons are sort of spread out as much as possible. But I think their dynamic range is enough, right? I think they can take even more triangles in 1 pixel. So these are also some of the back of the envelope calculation. Basically, there is a plot called Lavers plot, which what they do is they take every possible TPC ever built, measure their length and the resolution, and plot them and fit them. And then there is a function which is 5.7 times L raised to the power whatever, right? You tell me the number of segmentation, and they will tell you right away what will be the DVDX resolution. It works, right? I mean, there's really nothing going on there. It's as simple as that. And if you just use that, what you see is number of sigmas you can separate as a function of momentum for pi k and kp with a GridPix device. So it's really promising in terms of the PID, absolutely. And if you look at the tracking aspect of it, again, as I was saying, like the number of segmentation are so large, you can just gain like 35 micron to 240 micron resolution. It is extremely good even for a tracking device. So both the PID as well as the tracking can be done with the GridPix. Another important thing to note is when you put it in the magnetic field, the tracks bend. So actually the number of samples will increase, because now you are traveling more effective length within your gas volume. So that's the add-on, but which we haven't really considered in any of this calculation. So it has to work better than that, not in the other direction. Again, just to show what it will add to the EIC acceptance. So basically all these bottom islands we have put, I'll show you like what will be your PID range if the GridPix is included. But of course, it was for the Athena proposal. The design and things have changed, but that was the.
Sorry, so you're saying that was originally a part of Athena and then now will be like worked into
No.
Epic? Or...
We proposed it for Athena.
Oh, okay.
But Athena decided to go. They said basically it's too new technology. Mm-hmm. It's too much new method to trust on. So they put GridPix as a upgrade possibility. So in Athena, GridPix was an upgrade option. But since the review happened and everything, so Athena was turned down.
Yeah.
Right. So it doesn't really matter then.
But then is this considered a possible upgrade for Epic?
So no, so there is a possibility of upgrade for Epic.
Mm-hmm.
And also there is a discussion for the IP8 detector, which can come along. So for IP8, it can be a candidate, mm-hmm. But for Epic, it can be an upgrade.
Yeah.
But remember also one thing, people don't look for solutions until they see the problem.
Yeah.
And that's our best hope with Epic. Yeah. They haven't really simulated the tracking yet. So they don't know what the problem is. So they're not looking for the solution. But we are like confident once they will know that problem, they will look for the solution.
And who will they come to?
That's the deal.
Yeah,
right.
I see.
So that's the thing, because most of the simulations do not incorporate the background. Yeah. The beam background. It's still, I don't know the current. I mean, I'm not really up to date, but that was the problem. If you do not, like Nikolai has been advertising like
a little bit just now to finish this part of the report.
Yeah.
Really, just what was proposed. It was proposed detector with minimum mass. First of all, the record for TPC to have mass in any direction. doesn't matter, cathode, still cage, or readout. Because really first reaction was, oh, readout, it's huge mass, looking at normal standard PPC.
Yeah.
But GridPix is a piece of silicon.
Exactly.
And really just after all mass is coming only from cooling.
Yeah.
If you will fix exactly cooling, it's part of R&D.
Right.
It will be world record for any parameter.
Right.
So then once more, many times for many meetings, it was mentioned, guys, it's up what proposals now for EIC like official does not respond to request from Yale report. Because Yale report demands was cover all momentum particles starting from 1.1 GeV up to 10 GeV for bottom. But for looking for this report, can you see? Started from 0.3, 0.4
Yeah.
the best.
Mhm.
And his number, another number is crucial for this person. Number is not number, but 0.3. So really, if you're using this PPC with result, you don't need time of flight. It's huge save money.
Exactly.
It's difference factor 10 in cost. So it's a lot of politics, I would say.
Well,
Because-
yeah.
because this- Even this statement that really just it can be upgrade option,
Yeah.
it's absolutely wrong.
Yeah.
Because for setup and using only silicon, no place to install.
True.
Okay.
It's only in Europe can be done, but not that.
Good.
That is why it's very difficult to comment because
Yeah.
it's unpolitical.
Yeah, that,
So
Okay.
what's the R and D that you still need to do? It sounds like cooling.
R&D, yes, no,
But,
all of this,
so-
of course, from last point. R&D, first of all, demonstrate particle quantification. Because it's all time,
right.
so far, all the team working for,
Right.
linear collider, they have been is only in track.
Yeah.
So first one is just now demonstrate that really you can do PPC, particle quantification like a promise.
Right.
Mhm.
Number two is crucial to select gas. Gas,
Yep.
because once more, all measurements can be done so far for so-called T2K gas mixture. Who knows, maybe just using gases with smaller, let's say, D, is much
Helium
more
or
crucial.
something, yeah.
Because really, we can use up to helium,
Mhm.
because number of is so huge, even if you put it number 10 smaller, still it's very nice trick.
Right.
But particle application can be done much better, because why?
Right.
Because it's once more, first time in history, you measure not in,
Right.
in the yet, but the end for the number of electrons.
Exactly.
It's once more,
Basically
it's
counting everything.
improvement in particle application. First of all, you just completely can eliminate this delta electron reaction. You can see the delta electron.
Yeah.
You can put it out from your knowledge.
Yeah.
It's very nice. So
Yeah.
this is why many, I would say.
So there will be testing then.
There's been this,
It's in June.
where I really, they are using low momentum particles, and exactly like
It's in June,
in June, yes, absolutely.
2 weeks of June in Central.
We got, by the way, we got travel money for this. Testing. Somebody would like to join, please move your head. So really just,
Right, so I mean, it has many aspects for R&D, like some of them Nikolai mentioned. But there are a lot of other also, which is how you are going to read it out, right? There is a whole mathematical open problem. Like how to analyze it, how to interpret it, there are all sort of things. which are not yet settled really.
yes, one very crucial point. This TPC research result practically can be non-sensitive to any kind of synchrotron radiation.
Yeah.
It looks very strange, but it really can be done online.
Yeah.
Because synchrotron will produce a small cluster,
Yeah.
not track,
Mhm.
and can be eliminated even on online result.
Right.
So
So if
it's one
you
time.
really look at the event display, so what happens, like imagine in simple words, let's say you have a rectangular pad, right? I mean, the pad size is too big. So if a delta comes or a real head comes, they all look the same. Because your acceptance is just, the pad is so big. But in this extremely heavy segment, you can see this tight curve has to be a delta reactor. If you look at the event display from the bond guide, right? I mean, you can really, so the idea is it's not, it's kind of a tricky word when you say head-on blind detector, it's not like it's blind to head-on. But you can identify exactly where the head-on is. So that's what I think Nikolai means. Like it's not, it's sensitive to synchrotron, but you can identify the synchrotron. So you can really eliminate all the background from the, that's a cool feature of it. So we are very excited about it, and many people in Europe actually also. So by the way, LCTPC guys also wants to join us now. They just approached, so you know, a lot of people are actually adding to this effort.
So I think you're about, so we're on the hour, we've been interrupting you, so let me suggest that like, at this point, anybody who needs to leave because we've been here for the hour, that's what you said, right, and then and other people let's stay, because I'd like to hear what you've been doing on MOLLER and things, and other people can stay, but at this point, let's just thank Prakhar for the talk and let people leave gracefully.
All right, so halfway there.
Next one now.
But then it will go very fast now because they are less. All right, so the next topic, which sort of we are very much involved at Stony Brook, is the MOLLER experiment at Jefferson Lab. So it's basically you have a hydrogen at the target, liquid hydrogen target, and then you have a polarized electron beam. Look for the molar scattering, the polarized electron is scattered off of the electron from the liquid target, and then you sort of do your stuff. So basically, the motivation is to calculate the APV, which means the difference in the cross section in right-handed and left-handed neutrino, because if you flip the polarization of your incident electron beam, you will get two cross sections depending upon the polarization, and that sort of leads you to the weak charge coupling, and if you know that, then it is sort of related to the sinus square theta W, which is the weak mixing angle. So it's kind of a method to calculate APV to a high precision. So that's why in UAE also it's called high precision frontier. And the idea is to have a precision of 0.8 APV, which is extremely pure and precise. But the motivation of this measurement basically lies, does the standard model prediction, it will deviate from the standard model prediction or not? Because there is no data point with such tight error bars, and that's what that's one of the motivations for this. Now, what is the MOLLER experimental setup? Basically, we have a liquid hydrogen target, then there is a precision collimators, downstream toroid to sort of adjust the magnetic field so that the electron is scattered off in molar scattering, and the background scattered electrons can be sort of separated in R. And then there is a drift pipe tracking detectors where I will be sort of talking a little bit, and then there are integrating detectors which sort of integrates the quartz-based detector, and then there are fine detectors after that, and then you dump the beam. So our role is basically here, and the tracking detectors for the MOLLER. And the way they use these tracking detectors is interesting. That's why I thought to talk a little bit about it. This is sort of the zoom out view, like they have like 4 wheels. So these jam modules are mounted on a wheel. It's a circular, it's a 4-wheel station basically, and they have the capability to rotate and align. So you can decide to give them any orientation depending upon your needs. So the need is like it's a very high rate, it's the highest flux because all the precision experiments require high flux, and the position and angular resolution requirements were not really tight, as you can see. It's like 1 millimeter and 1 millimeter. So what they actually do is this. They have a production run and then they have a tracking run. They're two different things. So gems are not in the physics run when they are actually doing the experiment. They bring the gems in when they do calibration for their experiment. So calibration as in the optics, so beam optics. So once you have an electron beam scattered off, goes in, so you need a full transformation from where it started and where it ended, right? So that deep optics calibration they need to do if they change the energy or anything in the detector. So for that, they have a thing called sieve. It's like to hide basically. It has holes in that, and they are the high precision known positions. So they bring the seed in, so electrons can only go from these holes. And then they look at the gem plate and then do the reconstruction and say, okay, now I'm calibrated. I know where it is started, where it landed. And then they move these gems out and use the other quartz-based detectors to do the integrated mode of the thing. So when you do tracking, they put a thin carbon 12 foil instead of a liquid hydrogen. As you can imagine, if you're a thin sheet, you know exactly where you are. If you're a long target, you don't know where it actually happened. There can be more uncertainty if you have a longer target. So for calibration, they use the carbon 12 foil. They reduce the beam currents because high beam currents are not really good for gems, because they can actually sag the voltage on the gem foils and reduce the gain of the gem station. So they reduce the current flow in their experiment. And then they move the beam line, the gems in, the steel in, and then DAQ does in the counting mode, and that's how they sort of do the tracking. And when it comes to production, as you can see, they replace the target to the liquid long hydrogen target, and then the beam current goes off. Use 11 GeV beam because that's their main. And then jumps will be out of the beam line, seed will be out of the beam line, and DAQ does it in the integrator. So basically, you start counting the electrons on your scintillator detectors. So this is just to throw there's absolutely nothing new with these gem module production. It's a 3-gem stack. It has a cathode and readout is a UV stripe like that at an angle, is stereo angle, and nothing really unique about this particular configuration of gem. It's a 3-gem standard stack of operation. And this shows sort of one of the readout, like how the UV stripes are sort of looks like and what is the stack for this readout. But currently we are just, as you can see, we are just setting up for the stretching date for the gem foil, the gluing and all those things. But that should be running very soon, anytime now. And we have set up all the things for that. Then I'll quickly go through the pioneer experiment at PSI, which is also an upcoming experiment. It has been approved by the PSI lab in Switzerland. And it's very simple experiment if you look, but nothing which looks simple is simple. It has a calorimeter, it has a tracker, and it has a target. So only 3 detectors. It is small, little bitty. Right? The active target is 2 centimeter by 2 centimeter. Right? Now imagine that. The tracker, it starts from 3 centimeter to 5 centimeter. And the calorimeter is 9 tons. Right? So literally it's very, very simple setup in that sense. And most of the cost is because of the calorimeter, because liquid xenon. So anyhow, that's the main motivation. Again, it's a simple experiment. You have a 5+ beam, make it to decay in rest. It decays into an electron channel like a positron, or decays through a neon channel into a positron, and measure the branching ratio of them. And people, like when we started talking in our group and all, what, nobody has measured them yet, right? It's just pion decaying to electron and neon. How come it's not done? It's done, but not with very high precision. So that's the idea. So you look at this plot, it says most of the people come from G-2, so their plotting style is also like this. This is the standard model prediction, and this is the projected measurement they will do.
Yeah.
This is the current measurement, right? Exactly like G-2, the famous plot. Well, what do you do? And then there is another mode, which is sort of a pion decaying into beta decay channel. And that's extremely rare. Even the branching ratio stands for -8 for the second decay channel. So that's why they are projecting that for phase 2 and phase 3. But phase one will be for the first one. They will not have enough statistics to go to the second decay channel. But basically, the idea is if the lepton flavor universality is 2 or not, like so the Fermi constant for electron or for neon or for tau, is it all same like we call Fermi constant GL, or it varies for all these different leptons? And that's really an open question. There are many hints of beyond standard model physics and all those things. So that sort of motivates them to measure this thing, because it's very precisely calculated theoretical number. In the standard model theory, this is actually considered one of the best calculated number according to theory. So, and the error bars right now are like 20 times off. Like it's like hard to interpret anything at this time. So that is one of the motivation. And then of course they are also linked to the non-unitarity of the CKM at first row. Like the sum of these three is 1 or not. So that's another interesting consequence. So really, that's what I meant. It's not that simple. So it's a very famous thing to say, devil in the detail, and we call it in the tail. So devil is really in the tail, because if a pion decays to electron or pion decays to neon to electron, it's a 3-body decay. So you have a spread, right? In Michaelis spectrum is on, and then you have a back peak of the single decay. And then, well, was the big deal? They are different in energy, but what happens is that you have a radiative correction, and this tail really enters into neon as you include more things like, oh, neon decay in flight or decay in rest. That again adds an ambiguity, and all those contributions just make your measurement not precise. You have so much contamination get done there. So that's the problem they are planning to target. But actually, the catch in this whole experiment is the active target, which is the 4-dimensional tracking. Basically, it's a stack of silicon pixels, one after another. It's a stripe. There is stripes oriented in horizontal and vertical. It is a stack of them. So any event topology, like pion going to electron decaying because they all have their lifetime, decaying to neon, neon decaying to flight or in rest, you can do that event topology because it's just so fine. And it's just 2 centimeters by 2 centimeters. And then the calorimeter is the liquid xenon. They have been doing it. The past experience they had with the sodium iodide or the lyso crystal was that the material uniformity was not good. So the energy fluctuation was so much they could not measure it with a nice. They couldn't get the nice measurement out of their calorimeter. So this time they want to go 25 radiation length with liquid xenon. So they catch anything. And then there comes a tracker, which is also interesting in the sense what happens in some of the time, like you have a muon which goes out of acceptance in calorimeter. And that will add ambiguity when you are matching 8R with the calorimeter. So they want to really veto anything which does not go to calorimeter but goes to active target. So tracker will be kind of a vetoing detector for any outlying event, and it's a big contribution. And another thing is the pileup. Since these pion beams are extremely intense, right? So if you have a tiny information with this tracker, it can really help you to reduce the pileup because like double checking at 8R as well as on the track.
Are you producing pion beam?
That I'm not very certain because I'm not familiar too much with PSR. But I would guess they are just using some tertiary beam line and accelerate. I don't know. Yeah. That's how typically you do.
That's like or the can beam, right? Like the same thing.
Yeah, it should be. Well, as I said, I'm not certain because I don't know. But there are many experiments running. Actually, Muse experiment and all they are running there already. It does exist. Okay, so for this we wanted to go with resistive micro-RWELL detector because again they're lightweight. the readout can be integrated in the detector itself. You can make a cylindrical form or anything. And one of our main motivation was not just mu-RWELL is the best technology for it. The motivation was which technology will help to contribute in other experiments as well. So mu-RWELL is kind of a common technology which we are interested, and also in EIC it has a lot of space. So that's why we wanted to go with the mu-RWELL, not with any other detector technology. But it works, it's cheap, and it's doable. So what's wrong with that? The interesting thing we did with this is this. So there are like two mu-RWELLs, and then there will be a shared cathode. It's like a double-sided aluminum or copper, whatever. So, and then when the track goes in, you got two hits in both the layers at the same time. So the amount of material you are putting in front of your calorimeter is really reduced. There's really not much material, and you got two hits. So even single hits are always bad to have because you will lose them. But if you have double hit, it sort of really ensure your hit efficiency in that sense. And if you look at the side, that's how it will look like. It's a cylinder with a shared cathode running in a cylindrical shape, and it will surround the active target. So it will be on top of active target basically. So we have been very new to this experiment, like a couple of months. So we haven't got it yet, but our idea is we are actually designing right now the mu-RWELL design on a PCB so that the sun can produce, and then we are planning to test them. And particularly the timing, most of the MPGBs when we talk is mostly focused on spatial resolution, like in space, how much micron, how many micron. Not that much the timing, right? Because we say, okay, you can get 5 nanoseconds, but that's it. You cannot push there. So that's another dimension we want to explore with the different electronics like TDC and that kind of thing. Like how low we can go in that, because as fast as we can go is more better for the pilot with the pilot, because it just makes the sample very clean in that way. So that's one of the dimensions we are sort of looking at the time. So summary is just really, they are deployable in wide range of experiments. Some of them I'm personally involved. And there are many innovative ideas around, and many more will come also. It's not saturated yet. And future experiments like EIC, DNL, or first or second detector have a lot of space for R&D and new ideas. Not necessarily only for gaseous detectors, but LAPPD or silicon PMs or like PF-rich. There's just wide range of detectors which really needs expertise from the gaseous side of it. Thank you very much.
We asked all the questions, but if people have any other questions they want to ask?
Yeah, just quickly, you talked a lot about the sPHENIX TPC and why there are all these difficulties because it's small. Maybe I missed it, but what are the advantages of having a small? Like, why would you do that in the first place?
Because the bar magnet.
Sorry, because of the what?
So the problem is other way around. So the magnet sPHENIX used is
Oh,
called
okay.
bar magnet.
I see, yeah.
So we did not install it, but we took it from that. So it has a fixed bore size.
That was my fundamental contribution to sPHENIX, to save this magnet.
I think that's also why they have 2 layers of their HCal too, like one
Right, because jet program is a really big deal for sPHENIX, so that's why they wanted to go with inner HCal.
Just painful for me. I remember that sPHENIX TPC, when we discussed first time with Dick Mike and my guy from Stony Brook, we realized that really the same ion backflow, 0.3%, can be done with nice DEDX. So we propose such option, and really additional such option positive, the top gem will have not 4.5 kilowatt, but only 2.5. So battery will also cancel for some reason. Yeah, exactly. was our proposal, but maybe too late because main reaction from Tom Hennig, who is the leader of this one. We have no time, we have no time.
That's right, though.
So I will tell you one thing, like if you look at the timeline of different TPC's construction,
Yeah, sorry,
let's ask the question, how much time Alice took to build a TPC? Way longer than we did. Right? 5 years, give or take, you start to install. There is no time for R&D. Like for Sampa, we decided to go with the same electronics, what Alice used. The only change we had to make, like they had 3 options in the rise time, 80, 120 and 160, I think. So Alice used the other 2. We switched on the first one. So we used 80 as a rise time, 89 seconds. So, you know, we really did not have too much time to scratch. And this zigzag pad readout, we had a LDRD with DNL guys, right? You probably remember with Alexander and all. So this was even not done. We did not finish optimizing the zigzag, but we had to freeze because the company said, okay, we need 7 months to manufacture them. You can't keep doing R&D for 3 years and then 1 year of production and then you build the detector. So it was really rushed in that sense. You know.
But another proposal still alive. So what is specific transform for sPHENIX? Gas mixture cannot venture. It's very crucial for any kind of gas detectors when you have avalanche, you have UV light is coming and you would like to reduce this. Of course, GEM is more say, robust from this point. But nevertheless, still, even others TPC approach, time of the time they have something like what they have been checked. I would prefer to say spark, but really just very simple proposal, still in the front of this gate. Put additional 5, 10, 7% of CH4 in gas. 3 components, but not 2. An additional approval from the 3 components, once more, increase your ion moving speed. Once more, reduce a little bit your space shuttle. Okay, it's up to that.
Yeah, well, we will see. That's all I will say, like, you know, very soon. The engineering run will start, you know, in couple of months from now, so we will see. And it's not really that difficult to change the gas combination. It's hard to do anything on hardware. Gas is the issue.
But you would do that before you run, I assume.
So another interesting thing, just because you made that comment, most of the people think we have done the gain map and that's it. And that's the gain map I'm going to use in my calibration. Now, it changes. So really, most of the calibration comes from your cosmic or data, the tracks. That they are the real calibration. All the other things you do is just for stability's sake of thing, not really the input for your running sake of thing. Right? So even if you have to change gas, like Alice did 3 times, I think, right? They started with argon, moved to neon, then went to argon, and now they're back to neon, right?
No, it depends what kind of run you're speaking about.
Okay.
We had such discussion recently.
Uh-huh.
Because really, just all the changing possible back, it
Yes.
was happened during virus.
Uh-huh.
Virus chambers have been used and gating grid. And of course, in this case, neon is extremely, I would say, specific.
Yeah.
You have like neon light during your amplification. A lot of photos like that. That is why that they try to use neon and oh, mamma mia, it's like, I would say, bulb.
Yeah.
Instead of return back to argon.
Yeah.
But these gems, MOLLER, the main gain, of course, comes from the first one and last one, such specific water cylinder. That is why number, but it's smaller gain because last your gain is like multiplication all 4 steps. That is why number of these photons extremely low, practically very close. And that is why for gems, neon works nice, no problem. Others is using 3 components, and they're using CO2, and they're using nitrogen. Exactly from point of view what was mentioned, cleaner. Not only just tune your drift speed, everything, diffusion and so on, but parameter numbers frequent for any kind of gain data presentation. For some reason, the brain guys decided, okay, we can see why we don't. Okay.
The photos are interesting point, and we will see about that, right?
So when
So
you
I have
say
a
you can
general
change the
question.
test, you can't, what you're calling the engineering run is what the rest of the world is calling run 23.
Well,
right?
yeah, it's like,
Which is, so, but you can't change, like,
No,
how
I mean,
complicated to change the gas,
so-
maybe is my question, like, can you change during the run and turn off for a few days, or is it a month?
well, so okay, it really depends from where you start, right? So what our plan is, it's a leftover gas mixing systems from sPHENIX, which were supplying gas for HBD actually. Which is, HBD uses pure CFO, it has nothing, just CFO. And for CFO, you want extreme high standards of quality. You cannot afford water in there, hydrofluoric acid out. Oxygen goes in, you do get nothing out of it. So it's extremely sophisticated system for HBD. We are using the same system, which is equipped for 4 channels. Right, so basically you decide which 4 gases you want. So it's really turning on the channel, and you will have to do some R&D. So it's not that difficult. It's not like you have to take out a TPC or anything.
You have to flush it.
Yeah, you have to flush
Yeah.
5 turn, yeah, and so that's why our output has a low impedance path. So you can really flush like a hurricane.
So, totally different question. Early on, you mentioned microdots. I don't know what they are, but you have something that had dots. And I was
Right.
just curious
So-
about that.
So they, I think,
What it is
appeared
with
and
the structure.
disappeared. These
Yeah.
ones, I guess, right?
Yeah, so
Right.
what's what in that?
So I really am not expert on that, but my understanding was they are like sort of pins, right? Which
They're
is
like
stitched on.
tubes?
Yeah, like pin,
With a
needle
pin in the middle.
Yeah.
And then so you have a cathode.
Right.
on the outside of it.
at the bottom,
I
yeah.
understand it.
Right.
Okay.
So, but they appeared and disappeared very fast. I don't know if anybody ended up.
No, it's not completely dead.
I see.
Because the problem- because really,
I don't know.
problem only just, distribute your electrons, and you could not do it very small, I would say, pattern. Size of the cell, something like maybe
Mm,
5-6 millimeters. That's the problem for number of measurements, yes. But your size detector has been done, by the way, in Brookhaven,
mm,
in instrumentation, yes, I know
Not
that.
know
Guys,
I see.
so really, first one, and demonstrated really is working, how really the spin growing and discuss
Yeah.
everything. So in one small problem is discharge. And a lot of problem, because you have to do any kind of small, I would say, imperfections in your production,
Yeah,
something very, like, not dust, but really some small thing, some injection, and
some
you
matter.
never will keep high voltage. But Italian guys still continue this.
Really?
Yeah, so I
I
don't
see.
know what kind of experiment, but recently I did this.
I see. I really haven't heard anything lately.
And really for person who are interested in this one, in this month, in a week, it will be a CERN presentation exactly connected to any kind of micropattern detector.
Mhm.
Rui
Yeah,
will prepare this.
I see.
This meeting, and it's very impressive because it's nice laboratory as well.
Yeah.
So, sorry, CERN pioneering for many side detectors, and really just like final, I would say, presentation can be done and plan for the future.
Okay, thanks for coming in.